Module 3. Fundamentals of Blockchain and Distributed Ledger Technology. Lecture 2, ICT Systems for Decentralized Solutions, Part 2. In this lecture, we will cover the following topics: Internet applications, distributed and decentralized systems, Internet of Things, cloud computing and services. This lecture is part of Module 3, Fundamentals of Blockchain and Distributed Ledger Technology. With this lecture, you're going to learn how to apply the understanding of the client-server communication principle to explain examples of the principle in Internet communications. Indicate the characteristics of web communications. Discuss the operation of key mechanisms and application protocols for web communications, front-end applications, and application programming interfaces. Describe the difference between distributed and decentralized systems. Discuss the role of the Internet of Things and cloud computing in relation to DLT. The minimum requirements for this lecture are: running commands in the command line interface, installing software on your computer, Internet applications. The client-server communication principle is very common in Internet applications. It requires two complementing application layer processes using the same application layer communication protocol. The protocol defines the format of the request and response. The client entity requests resources and actions from a server. The server processes the request and returns responses to the client. One server can serve many clients at the same time. Web applications are an example of client-server communications. A web browser is the client software and, example, Apache server-side software. They communicate through the TCP/IP communication stack and the Internet. They communicate with the HTTP protocol. The web browser sends HTTP requests, and the web server returns HTTP responses. Many other Internet applications apply the client-server principle. Dedicated application protocols are used in specific applications. For example, SMTP for the exchange of emails between email servers, SSH for secure console access of remote computers, FTP for file transfer, and SIP to initiate voice-over IP calls. Peer-to-peer, P2P, is an alternative communication principle. In P2P, all the communicating entities are equal. They can create requests or respond to them. There is no central entity, server, in P2P. P2P is the fundament of file-sharing systems and also a key part of communications between blockchain nodes. How does this apply to DLT? Blockchain nodes and decentralized applications employ CS and P2P principles. The communication between distributed and decentralized blockchain nodes requires P2P. Other parts of decentralized applications, example, APIs and web interfaces, are CS-based. A Uniform Resource Locator, URL, is a reference to a resource on the Internet. It is comprised of the domain name of the computer where the resource is located, protocol to request and retrieve the resource from the server, asterisk, listening transport port at the server, asterisk, directory path and the name of the resource, asterisk. If omitted in an URL, the protocol and the corresponding well-known port of the server are selected by the browser. If omitted, the server can respond with a predefined default resource, example, index.html page. A web address is an URL pointing to a web resource. Web client and web server communicate with HTTP. There are many implementations of web browsers, but the basic operation is the same for all of them. The user selects the address, URL, of the desired web resource by clicking a web page link or entering it in the browser's address bar. The browser builds an HTTP request, and the host transports it with TCP over the Internet to the server. The server processes the request and returns the response to the browser. In the response, there is the requested resource or a notification about the request processing error. The browser renders the received resource and presents, example, the web page, to the user. There are different communication methods supported by HTTP. Based on the method selected, the client can indicate to the server what action it wants to impose on the resource. E.g., the GET method retrieves and POST uploads a resource. The DELETE requests the removal of a resource from the server. Server configuration and access control determine which methods are supported and allowed in a request. Web servers support at least GET and POST. HTTP-based API servers can support other methods, too. HTTP requests and responses have headers and bodies. Headers specify the details of a request or a response, the resource name, method, resource format, timestamps, request processing status codes, and so on. In the body, there is the content of the retrieved or uploaded resource, example, an HTML or an image file. The HTTP protocol is not confidential. It provides no encryption of the content in the bodies of requests and responses. Anyone intercepting the datagrams with HTTP messages can see the content of the resources. This endangers the privacy of communicating parties. HTTPS secure is the solution for confidential web communications. HTTPS is not really a separate protocol. It is rather explained as a tiny additional communication layer placed between the HTTP and the underlying TCP. The security protocol applied in this layer is Transport Layer Security, TLS. The HTTP has an upgrade mechanism to initiate TLS over an existing TCP connection. TLS encrypts the HTTP messages. TLS is an improved version of the Secure Socket Layer, SSL, protocol, which is deprecated due to security flaws. HTTPS, TLS, encrypts all message contents, including the HTTP headers and the request/response data. TLS requires encryption keys to be exchanged for each session. For trusted communications, servers or /n clients might require authentication during the TLS session establishment. With digital certificates, servers and clients are identified, authenticated, and authorized to access web resources. How does this apply to DLT? If possible, use HTTPS in decentralized applications. Bear in mind that the HTTPS servers listen on different transport ports than HTTPS. The well-known port for HTTPS is 443. If you replace HTTP with HTTPS in an application, ensure that the network security settings do not limit access to it, example, company firewall. The HTTP protocol supports various content types and subtypes of web resources, text, image, audio, video, or application, representing any kind of binary data. A subtype of text content is HTML. Hypertext Markup Language, HTML, is the way to implement web pages. HTML combines the content of the page with formatting tags, markups. With tags in HTML, we can define the structure, headings, tables, lists, and the look of a web page, colors, fonts. The World Wide Web Consortium, W3C, is responsible for HTML standardization. The latest specifications for HTML5 can be found at http://www.w3.org/tr/html5/. Another subtype of text content is various semi-structured data formats, such as JSON or XML. Because of text type, these documents are in a readable form but are not meant to be digested directly by a human. They enable data exchange from and to the programming interfaces in web applications. Tags or other markers enforce hierarchies of records and fields within the data. This gives them a self-describing structure. Such data can be easily encoded or decoded automatically. JavaScript object notation originates, JSON, from the JavaScript programming language, but soon became the dominant web-based API resource format. Other structured data formats are applied for web communications, example, XML and JAML, but less frequently than JSON. How does this apply to DLT? The JSON format is frequent in decentralized applications. It is used in web APIs of blockchain nodes. JSON strings can also be included in blockchain transactions. For example, input parameters are encoded in JSON when sending a transaction to invoke a function in an Ethereum smart contract. The resources in a web server can be static. The content of the resource is stored in a file. When requested such a resource, the server reads and returns the content in the file in response to the client. With dynamic resources, during the request processing, the server executes a code that builds the resource for each request. A resource is, therefore, no longer static but is the result of the executed program logic and the input parameters. This principle is called server-side programming. In that way, a server can, example, query its database, select only the set of items added to the database during the period, which was given as an input parameter by the web user, and return the selected list in the response. Server-side programs can be developed in different programming languages. Servers can have much larger system resources than client computers and can process even very complex algorithms or analyze large quantities of data. The web client renders the received resource in the same, regardless of its static or dynamic origin. The dynamic resources can have all content types supported by HTTP, including, example, HTML, JSON, and images. How does this apply to DLT? Dynamic server-side content is prevailing in web-based parts of decentralized applications, just as in traditional web applications. Static content remains appropriate for, example, simple web pages, images, videos, or downloadable files. Apart from rendering the content of web resources, web browsers can execute the programming code received from the servers. This code is written in JavaScript. Unlike server-side dynamic programming, JavaScript is executed in a browser. The browser is a sandbox to execute this code in the client securely. The client-side code can communicate with web APIs or change the appearance of a page already displayed in a browser. Client-side programming with JavaScript assures very low latency because user inputs can be processed locally and sent to a server only if needed. How does this apply to DLT? Client-side programming and the application of supporting web APIs are the fundaments for applications running in a browser, example, web-based smart contract programming tools or IoT devices connected to web servers and resources. HTTP proved to be versatile and is therefore not used only to communicate with websites. It is also used as a general application mechanism to exchange resources and access remote services over the Internet. Application Programming Interface (API) is an access point for integrating application software to access the features or data at different parts of the application. In web, APIs serve web resources, and the interfaces are accessed with the HTTP protocol. Web APIs are indispensable in modern web applications. Web APIs can be contacted directly by browsers, end-user clients, or web servers. After a single-page rendering web page is rendered in the browser, it connects to a server API for the supply of new data to be incorporated into the page when needed. This occurs in the background, without a reload of the page initialized by the user. From the Web API, the page receives the data in some structured format, example, JSON, and the JavaScript code in the browser keeps constantly updating the page. An example of this use is a web page that allows for infinite scrolling. Another use of web APIs in a web page is combining the content from different servers. If you include, example, a digital map on your page, it can be retrieved from the API of the digital map provided and seamlessly embedded into your page. Web servers might access the APIs of other servers while executing their server-side logic. While building the response for the client, a server obtains data or delegates processing services to other servers. There is no common approach to how a web API must be organized. The documentation of each API provider clarifies what communication protocols and data formats are supported and how the access control is organized. How does this apply to DLT? Web APIs are indispensable for integrating the building parts of decentralized applications. For example, all the functions for managing the blockchain network, using accounts, or creating transactions can be reached over a web API integrated into an Ethereum blockchain node. HTTP proved to be versatile and is therefore not used only to communicate with websites. It is also used as a general application mechanism to exchange resources in, example, web APIs or in web streaming of video and audio. The client-server nature of the HTTP may be a limiting factor in, example, web APIs or in web streaming of video and audio because of the protocol overhead, latency, and the mandatory request-response sequence. Therefore, the WebSocket protocol was defined as an upgrade of the HTTP in RFC 6455. The communication between a client and a server starts with a regular HTTP. If both parties agree, the communication can be upgraded to WebSocket. The HTTP thus initializes the WebSocket session. The WebSocket session utilizes the same transport ports as HTTP and works with HTTPS, too. WebSocket enables a full duplex two-way channel between the communication parties. Once upgraded to WebSockets, any party can send the data when needed and not as a response to a previous request. The WebSocket messages are simpler than HTTP. This reduces the overhead and decreases communication latency. How does this apply to DLT? APIs and decentralized solutions may support WebSockets. If you need an efficient bidirectional communication service with an API, consider the use of WebSockets in your applications. While some web resources are meant to be freely accessible, others need restricted access only for authorized users. For example, a public news page imposes no limitations on who can access it. A university study system strictly separates students, professors, and the student office. Each user can only perform actions enabled for their role in the student management system. Efficient access control is, therefore, a key security feature of such a system. Users have to be uniquely identified to control their access to web applications and resources. Web cookies are an identification mechanism in the HTTP protocol, which requires no authorization. It is solely used to distinguish between users accessing a website and identifying a user who has accessed it in the past. Other identification approaches include usernames or email addresses. Authentication assures the authenticity of a provided identity. Identification and authentication are frequently made in one step, example, by providing a combination of username and password or using a digital certificate to sign into a website. Once a user is identified and his identity authenticated, the server can provide resources to the user based on the authorization policies it uses. In the silos approach, access control is centralized and provided by each web application separately. For example, username-based access control in an online forum. In a federated approach, big social media sites also act as authentication providers for other online sites and resources. The authentication service utilizes the OAuth 2, commonly applied in web application development. This might be convenient for smaller sites and their users. However, the federated solution gives additional unwanted insight to the authentication provider into users' online activities. How does this apply to DLT? Self-sovereign identity, SSI, is an alternative approach to digital identity and authorization. Unlike in the federated approach, users remain in control of their identities and the data they share. Blockchains can be a vital part of SSI operations. Distributed and decentralized systems. An element of an ICT system can be distributed into several entities. The distribution can have different motivations, e.g., reaching the performance, example, when running a web application on more servers, when a single one no longer provides the required resources. Server loads can be balanced among the available entities. Providing minimum delays for the users while accessing the services, users contact servers in their geographical neighborhood. Availability of a system and robust service provisioning. A distributed system might be fault-tolerant, meaning that it continues to operate, even if some instances cease to operate or become unreachable due to communication failures. For this reason, example, computers in an airplane are multiplied. Being able to decentralize the control of the system. Distributing a system imposes several relevant challenges. We need a capable communication network to interconnect all the distributed entities. There are network and processing delays in propagating the information within the distributed system. Independent distributed entities must be synchronized to maintain the same view of the data they provide. Due to network delays, some parts of the system might be, temporarily, out of sync. There can be faulty or malicious entities in the system, jeopardizing synchronization, data consistency, and service provisioning. Costs and resources to maintain a distributed system may become relevant. How does this apply to DLT? Distributed ledger technologies derive their key features from their distributed nature. The prerequisite for decentralization is the distribution of blockchain nodes and efficient mechanisms to maintain the consensus about the system's state, even in case of a limited number of faulty or malicious nodes. Decentralization is required to provide trust without having a central trusted entity. There is no central trusted entity in a decentralized system. The lack of central trust in DLT is replaced by the distribution of entities in a way that no one controls the majority of them. In these systems, the collaborating entities do not a priori trust each other. Despite this, they need to cooperate to maintain the common truth, i.e., the content of the distributed ledger and appending new data, example, blocks to it. Decentralization is required to provide trust without having a central trusted entity. Decentralization is about the governance of parts of the system. Distributed nature is the prerequisite for decentralization in DLT. A consolidated system comprising only one, or a low number, entity cannot be decentralized. In this respect, distribution refers to the system's topology, example, the blockchain network. For illustration, a modern database can be distributed to increase its performance, resilience, and availability. But all its distributed parts are still managed by the same database administrator. It is, therefore, not decentralized. In this case, the distribution was not applied to provide decentralized trust, but to other positive features of a distributed system. To trust the content of the database, we need to trust its central owner. In DLT, trust is assured by decentralization and sophisticated cryptographic mechanisms. One of the key challenges in blockchain systems is achieving a consensus about appending new data to the ledger. The consensus must be reached among all the participating nodes in the network. Some of the nodes might be faulty or malicious. The consensus information must be spread among the nodes to avoid network partitioning. Network convergence becomes challenging due to network latency, especially if there are many nodes in the network. How does this apply to DLT? It is essential to clearly distinguish between a system's distribution and decentralization. Distributed nature is the prerequisite for decentralization in DLT. There are many examples of distributed ICT systems because of the favorable features of distribution. The Internet itself is highly distributed. Numerous routers are building the Internet core communication infrastructure and are connected with numerous alternative connections. The Internet and routing protocols are designed to glue this distributed physical infrastructure into a common Internet. Distributed networks can be created with application layer protocols, too. Because they reside atop the Internet network layer, L3, they are called overlay networks or logical overlay networks. Examples of logical overlay networks are peer-to-peer, P2P, file-sharing networks, such as BitTorrent. The Tor network enables personal privacy while accessing web resources. The overlay network is composed of about 7,000 relays, the Tor nodes. Public blockchain networks, such as Bitcoin or Ethereum mainnet. All these distributed overlay networks are decentralized, too. How does this apply to DLT? Distribution and decentralization are not unique to blockchain networks. There are several motivations for creating a distributed overlay network, including increasing the performance, assuring availability and robust service provisioning, or decentralizing the system's control. We can share many findings about other overlay networks to understand blockchain networks better. Internet of Things. In the Internet of Things, IoT, the devices are no longer user terminals but become self-sufficient entities, able to interact with the environment, process data, and communicate over the Internet. Interactions can occur directly between the devices in a machine-to-machine, M2M, manner. The number of IoT devices is no longer related to the population density, on the contrary, the number of mobile phones is. They can therefore collect immense quantities of data, which is the source for big data and advanced data analytics. IoT's key business sectors and application domains are smart cities and homes, smart cars and mobility, Industry 4.0 and logistics, agriculture, waste management, and environment-related applications, and health and personal well-being. An IoT solution for agriculture can collect various environmental parameters from field sensors. The data is sent to a cloud analytics service, which alerts the farmer and predicts the measures to be taken, example, additional watering or finding the optimal timing for adding nutrition. The system can operate autonomously without human intervention. How does this apply to DLT? With DLT, devices can become economically independent entities that can acquire and purchase services from other devices through the decentralized application. Smart contracts support business logic in the IoT device operation. This facilitates innovative business cases, such as servitization in Industry 4.0 and other application domains. IoT systems are described with a three-layer IoT architecture model. These layers are not to be confused with the layers of TCP/IP. At the perception layer, things, example, a refrigerator, car, or parking spot in a city, are equipped with sensors and actuators to interact with the environment. Embedded systems are incorporated into the device to provide communication and computation capabilities. A device connects to cloud services through the communication layer, where the Internet Protocol connectivity can be applied, and the same physical networks are used, i.e., wired, wireless, or mobile, as for computers or mobile phones. There are also dedicated mobile and wireless networks for IoT. They provide physical connectivity customized for IoT. The application layer in IoT collects and analyzes data and provides configurations, feedback, and visualizations. This layer usually comprises two sublayers: the dedicated IoT cloud platforms and the application logic built on these platforms. Based on the device's capabilities and limitations and the requirements of a particular IoT application, deviations from this general architecture are possible. How does this apply to DLT? When adding devices to a decentralized application, we have to consider and combine their roles in IoT as well as in the decentralized application. IoT devices may impose specific requirements on the underlying communication networks. They derive from the number and device density, machine-to-machine communications, computational constraints, or energy consumption. IoT devices do not require high bit rates in communication if they, example, once in a while, report a small amount of sensory data. On the other hand, the entire communication of a device has to be extremely optimized, if it is battery or solar powered. The traditional mobile and wireless networks do not allow for this optimization. We have therefore dedicated low-power, long-range wireless technologies and networks, example, LoRaWAN, and extensions of mobile networks, example, NB-IoT in 4G, 5G, specialized for the IoT. An IoT device can also use a short-range, low-power wireless technology, example, Bluetooth. It then connects to a capable communication gateway, which provides internet connectivity. Some IoT device communication characteristics affect network operators and other IoT application developers. How does this apply to DLT? IoT devices' communication and computation constraints direct the design and implementation of machine interfaces in a decentralized application. The device might not be capable of performing all the required blockchain functions. Often, compromises are needed due to device constraints that may affect decentralization and security and, thus, trust in the decentralized application. Cloud computing and services. Cloud computing is the ubiquitous, convenient, on-demand provision of computing capabilities, such as server time, network storage, applications, and services. These capabilities are available over the network. Cloud systems automatically control and optimize resource use, which makes them more efficient, reliable, and adaptable than traditional provisioning. Capabilities can be nearly instantly scaled with demand. Cloud systems can be public and deployed by cloud service providers. Private cloud deployments are being used, owned, managed, and operated by a single institution. Private clouds, too, optimize resource use and facilitate flexibility. Due to their smaller scale, they are not as efficient as the large public clouds. Still, they increase security and data privacy, reduce latency when accessing the resources, and minimize vendor lock-in. In hybrid deployments, we combine public and private cloud infrastructure to obtain the benefits of both. Any cloud deployment model requires some form of a data center to house computer systems and resource virtualization to utilize these systems efficiently. How does this apply to DLT? Cloud systems are indispensable for the implementation of decentralized applications. Frequently, we rely on different cloud deployment models to assure the required level of distribution, decentralization, and expected trust. A data center is a physical facility hosting computers, disk arrays, and capable networking for their interconnection. The communication networks can be Ethernet and IP or specialized storage area networks with dedicated fiber channel technology. A key to efficient data center operation is reliable power supply and cooling systems. Data centers provide various services, such as colocation, dedicated hosting, virtualized dedicated hosting, or virtualized services. In colocation, users install their physical computers and predominantly benefit from the data center's reliable power, cooling, and network supply. In dedicated hosting, the provider assures and maintains a dedicated physical computer. The provider enables virtual computers or even particular virtual services in virtualized hosting. The large scale of a data center reduces the costs, and careful design assures reliable and scalable operation. Virtualization enables efficient use of resources and minimizes maintenance costs. Public cloud service providers run their data centers. These facilities can host several million physical computers and consume over 100 megawatts of power. Large service providers run several data centers all around the globe. How does this apply to DLT? We might need just a small server room and accommodate only a couple of computers to run some parts of our decentralized application. We still have to consider the architecture, redundancy, and networking and carefully design the power supply and cooling to make it efficient and reliable. Cloud service providers offer various flavors of virtualized services. These can be used as end-user services or as parts of application development. We can, therefore, flexibly select a service model that best fits our needs. This match combines the desired functionality in service use or flexibility in application creation and handing over the underlying technology maintenance to the service provided. The service models are frequently labeled as, example, IaaS, PaaS, or XaaS. While the first letter denotes the model, as a service, AAS, indicates servitization. Infrastructure as a service, IaaS, provides general processing and storage capabilities. It leaves the application developer full flexibility in selecting, as well as the responsibility to manage and maintain the operating systems and applications that base on IaaS. Platform as a Service, PaaS, arranges online platforms for application development. These are, example, databases, MongoDB, website creation platforms, WordPress, or IoT platforms, ThingsBoard. When using PaaS, we can focus on our data and application only. The service provider maintains the platform and assures its availability, security, and scalability. In Software as a Service, SaaS, users obtain cloud equivalents of desktop applications, example, web-based office tools or online disk drives. Service is accessed through a web browser, so no software installation is needed by the end user. Besides, all the user-created content is stored online, too. Backend as a Service, BaaS, cloud service model lets developers focus entirely on writing the front-end application code. The service provider procures the backend services accessible via APIs and software development kits to utilize them. The developers thus employ all the backend functionality they need without building the backend themselves. However, relying on service providers' SDKs usually locks the solution to a specific service provider. In Function as a Service, FaaS, the developers consume particular function executions. This model is used when building microservices applications. Other cloud computing and remote access service models are appearing, example, Security as a Service, so nearly every ICT aspect can be delivered as a service, Anything as a Service, XaaS. How does this apply to DLT? The Blockchain as a Service, BCaaS, model is specialized for decentralized applications. It enables blockchain node and network deployment, system monitoring, smart contract analysis, and testing. Frequently, it assures efficient access control for permissioned DL networks and is therefore suitable for private and consortium blockchain networks. Major BCaaS providers predominantly build on Hyperledger and Ethereum technologies. Containers are a form of virtualization, too. They are used for deploying and managing software. Containers are packages containing all the necessary elements to run in any environment. Apart from the applications, a container packages all dependencies related to the application software, runs them in an isolated environment, and abstracts applications from the physical environment in which they are running. Containers can be executed in performant private or public cloud computing environments, which manage networking, load balancing, security, and scaling. On the other hand, if the resource requirements are not high, we can run containers on the developer's personal computer. Containers are a convenient way to run server-side applications. Various execution options facilitate swift migration from the development to a performant production environment. How does this apply to DLT? Parts of decentralized applications, example, blockchain nodes and web and API servers, can be packaged, distributed, and executed in containers. In this way, we can focus on the operation of the decentralized application and reduce software maintenance work. An IoT application may require a refinement of the cloud-centric IoT architecture, which foresees rather simple IoT devices and all the data processing and application logic in cloud servers. The complementary approach is called fog or edge computing. Two underlying concepts are driving the shift toward fog architecture. Some IoT devices can efficiently process local data, including real-time video. This eliminates the need to upload all the device's data to some server to store and analyze it. Some IoT applications require very low latency, real-time operation, which cannot be met if all the data is transported to a remote server for processing. Shipping all the device data to cloud systems may also cause excessive and unnecessary network load. To maintain data privacy, we often do not wish to share all the data with a cloud service. The terms fog and edge indicate that a part of the processing is executed closer to or in the device. This approach does not replace the cloud concept, but complements it. In fog computing, there are cloud servers and applications, too. But the application designers decide which part of processing is made and what data is stored in the cloud or locally. How does this apply to DLT? With IoT devices in decentralized applications, we have to define which blockchain-related functions will be performed in the device and which in network nodes. E.g., a transaction can be created and signed in the device if it is capable of securely keeping the encryption keys and running encryption algorithms. Otherwise, the device can create an unsigned transaction and submit it to a blockchain node for further processing. Thank you for listening to this lecture.